Hi, it's Guillermo. Today we are going to talk about one kind of problems that we are going to find in hundreds of different situations. Logistic, financial task, or industrial process. The QUBO problems, quadratic unconstrained binary optimization. So today we are going to see what are these kind of problems, how we can codify them, and how we can solve it in a quantum computer. To understand this concept, through all the video we are going to use a practical example. So let's imagine we are a company that organize events. In particular, this weekend we have to schedule 5 different events that are going to take the whole day. That said, if 2 events are in the same day, one person can't go to both, have to choose between one or another. On the other hand, we are given a list of the people and the 2 events that they want to go to. Let's say, for example, the person number 1 want to go to the event 1 and 4. The person number 2 want to go to the 2 and 3. The person number 3 want to go to the events 4 and 5. And finally, let's say the person number 4 want to go to the event 3 and 4. So the final question is how we have to schedule the events through the weekend in order that these people can go to the preference that they choose before. Because if 2 events are in the same day, as I say, they can go to both of them. The cool thing about these kind of problems is that there is an easy way to represent it with a graph. In our case, the nodes are going to be the events. In that case, we have 5. And the edges are going to connect the preference of each person. It means we are going to connect the node 1 and 4 because the person number 1 are interested to go to both of them. Also, in order to represent our solution, we are going to paint in white the nodes, it means the events, that happen the Saturday, and in black the ones that happen in a Sunday. So our final goal is going to find the best color configuration that maximize the number of attendance to our events. So if we pay attention, what we are trying to do is maximize the number of edges of connection between nodes of different color, because it means that the both preference of a specific person happen in different days. In our particular example, we are going to have 5 different variables, x1, 2, 3, 4, and 5, where, for example, x3 is going to be equal to 0 if the event number 3 is on Saturday, and is going to be equal to 1 if the event is a Sunday. It will be the same than the colors, but with a binary representation. So, in order to optimize something, actually, we need a function f that depends on these 5 variables that tell us how many events our people are going to be able to go to. So if you want to think how is the final expression of this f function, this is the perfect moment to pause the video, because now we are going to show the final solution. This is our f definition, where each line represents the amount of events that each person is going to be able to go. So let's understand this expression. In the first line, we are going to say that by default, the first person is going to be able to go to one of the events, because if they are in the same day, at least this person can choose one of them. And then we need to add 1 if the 2 events have a different value. If one is on Saturday and the other is on Sunday, we are going to add 1 to the expression. And you can check that in this particular example, x1 plus x4 minus 2 times x1, x4, if the 2 variables have the same value, this amount is going to be equal to 0. But if they have different values, the amount is going to be equal to 1. So we have all the ingredients to understand what is a QUBO problem. First of all, we say that the Q comes from quadratic, and it means because our final expression, this f function, the maximum degree of the expression is 2. The U means unconstrained, and in particular this is a problem that has not any constraint. Anyone is told us this event has to happen a Saturday. We have completely freedom to do our configurations. The B comes from binary, and our variables take only 2 possible values, 0 or 1. This is a binary problem. And finally, the O comes from optimization. Of course, if we are trying to find a maximum or a minimum, this is an optimization problem. So now that we already have this mathematical formulation, we need to start to think in how we can insert this in a quantum computer. Actually, a quantum computer doesn't like too much work with this binary representation, with 0 and 1. Actually, it prefers work with a binary representation too, but the numbers 1 and -1. In particular, it's very easy to pass from one to another. We only have to do this change of variable, where x sub I is going to be equal to 1 minus z sub I divided 2. In that case, z sub I is going to be equal to 1 if the event is on Saturday, and is going to be equal to -1 when the event is the Sunday. This will be our final expression with these new variables, but we still have to do one step more. We have to turn this expression into a Hamiltonian in such a way that, given a specific configuration, if we estimate the expected value over this Hamiltonian, the result has to be equal to f with this specific configuration. I know it could sound very difficult, but you are going to see that the process is very easy. The only thing that we have to do is swap these set variables for Pauli set gates. In particular, for example, if we have the expression set1 times set4, we are going to swap that for Pauli set in the qubit number 1, tensor product Pauli set in the qubit 4. And now that we know all the theory, let's go to the notebook and see how it works. In the description of the video, you are going to find a link to the notebook, so it's going to be easy to follow. So now we are going to start with a quick summary of the things that we just explained. We are going to have 5 different events, 4 people, and some preference of our people and the events they want to attend. After that, we introduced the binary formulation, where x could take the value 0 or 1, and it depends on the date we are going to schedule these events. That gives us this formulation. After that, we explained that a quantum computer prefers work with ones and -1s, like binary variables. So with this change of variable, we get this formulation that we can say here. So now we have to build the Hamiltonian associated with this function. In particular, to do that with PennyLane, first of all, we have to import our library, and we are going to import numpy from PennyLane, as we just see in another videos. So now, this Hamiltonian is built just swapping these set variables for Pauli set. In the case of this first number, we have a 6 without any variable, so we can just put any identity operator that we want. So we are going to choose to do a identity over the first qubit. Then subtract 0.5 times QML Pauli set in the first qubit, because here we have a set 1, tensor product Pauli set gate in the 4th qubit. So if we do that with all the elements, we are going to have this final Hamiltonian. Actually, the problem that we are trying to solve is maximize a expected value, but we are more familiar with the minimization. So the only thing that we have to do is change all the signs of the elements of the Hamiltonian. So if we change these signs, now our new problem is going to be minimize the expected value over h. The next step is build the circuit that, given initial configuration, is going to return the expected value of this Hamiltonian. So this circuit is going to be run in one device, that the C is the default qubit. The wires that we are going to use are the wires of the Hamiltonian, so we just can write 8 wires. So now we define the Q node. That is the way to say that our circuit is going to be run in that device, and we create the circuit. That depends on some parameters that we are going to codify in rotations over the y-axis, because this is a particular good gate when we work with real numbers. So now that we have our circuit, we can check that it works just trying an example. So let's guess our configuration is going to be 0, 0, 0, 0, 0. It means all the events are going to be the Saturday. This is equivalent to say circuit, where we are going to say to send these 5 angles, rotations. In this case, we get -4. And this is the expected behavior, because if all the events are in the same day and we have 4 people, each of them are going to be able to go to just one of them. And finally, we have to put our function, this circuit, in a training process. So to do that, we need 3 things: an initial value for the parameters, an optimizer, and the number of epochs. So with that, we can code the main idea of the training. In our case, we have chosen the Adagraph optimizer and 200 epochs. So after this training, we get that the energy, the expected value of our Hamiltonian with these specific params is going to be -8. So now we have to check in some way what is the configuration for this specific energy. To do that, we have to do a little modification over the circuit function that we defined before. In that case, we are going to copy this cell and paste here. And now, instead of ask for the expected value of the Hamiltonian, we are going to ask for get a sample of the configuration with a specific parameters. In that case, we have to define the number of shots that we want, and we only want one configuration, so let's see, shots equal to 1. So finally, we are going to ask for the sample with the final params that we just calculate. So if we do that, we get our solution 10101. That it means that the events 2 and 4 has to be in the Saturday and the other ones the Sunday. So congratulations for solving your first QUBO problem in a quantum computer. But just to say that this is the beginning. There are a lot of more to learn about this kind of problems. There are more advanced algorithms like the QAOA, or even we can add constraints to these problems when the QUBO definition means unconstrained. So I invite you to keep learning about this topic, subscribe to the channel if you are interested in it, and I see you in a next video. Thanks for being there.